Greetings. I am Satyajit Meti, undergraduate fourth year at IIT Madras. My co-authors are Rohan Ramachandran, undergraduate fourth year at Amrita Vishwa Vidyapeetham at Madai, and Professor Narayanan Pomrat of Takshashila Institute, Hampton, Virginia, USA. Climate prediction using computational simulation will demand deep learning. This necessitates massive amounts of meteorological data collected continuously over the oceans. This requires high-altitude, long-endurance stratospheric platforms called flying leaves. In turn, those platforms require an assembly of smaller vehicles which we call flying leaflets. This paper is about the aerodynamic and structural design and flight simulation of an 8-meter span solar-powered 25 kg vehicle with 400 kilometers of daytime range. We are presenting here not as experts on AI or electrical engineering, but to invite you to participate with your expertise. I'll first show you a video about the project itself. So this is a flight simulation of our 8-meter span solar-powered long endurance biplane weighing 25 kgs. It is seen flying over the Kerala coast just west of Tadupasheri Kochi International Airport. This flying leaflet is made of carbon fiber. As you can see, this is the initial takeoff phase. It can take off from a Kerala beach. And here comes the landing phase of our mission. Our UAV can land on a concrete pavement or even beaches. This is a mission plan. The route map starts at the beach near IT Madras. Other points are beaches separated by 2 to 4 hours driving time. These are the stations during our mission. And this is our final destination, Kavarati helipad. And here is an initial geometry of the vehicle. As observed even in the previous video, the lower wing is covered with solar cells to drive two brushless DC electric motors with propellers. These two BLDC motors with propellers have an electronic speed controller which collectively provides fast response to your control in addition to providing thrust. The upper wing is a thin mylar sheet supported on a carbon fiber frame. We set the design weight at 25 kgs to challenge the structural design, but we have flown with up to 38 kgs, so there is a plenty of scope for meteorological payloads. We can't carry typical instruments for the troposphere and tropopause and even for the stratosphere. We are using flight simulation in the design loop, starting with an initial configuration. Once a stable configuration is established, we use computer-aided designing to draw the parts and use that to calculate the total weight and center of gravity location. Flight simulation establishes the profile drag coefficient, which is usually the most difficult property to find and usually requires extensive wind tunnel testing with subscale models. So this process enables huge savings in the design process, compressing it from several years to just a few months or weeks. Different types of results are given in the paper. In summary, design point calculations using a Python computer code gave the parameters that were used in flight simulations and validated initial assumptions regarding the performance parameters. Simulation results gave the desired range of dimensions within which the center of gravity had to be located. The computer-aided design using Autodesk Fusion 360 gave the weight and verified the center of gravity. The design was iterated until the weight and CG were in a satisfactory range. We did validate against various sources, including existing high-altitude long-endurance vehicles. Lifting sheet makes our overall wing loading very low, so that the speed and the lift coefficient are very low. So hence, there is no need for very high aspect ratio. Our structural weight estimation was validated against what the HALE vehicles achieve routinely. We are addressing the remaining design uncertainties now. The Explain 12 is a full physics flight simulator including solar power variation models as well as detailed aerodynamics and flight mechanics, but only rudimentary structural strength modeling. So the primary aim is to get the structural weight verified both in static and dynamic simulations and determine the actual limiting acceleration values before the failure occurs and what the failure mode is, first failure mode is. Other steps to reduce uncertainties are summarized in the slide. The results show that we can execute the mission. Speed, altitude, and climb rate are shown to be more than sufficient, indicating the availability of enough solar power. Takeoff and landing on beaches is shown to be viable. The weight limit can be satisfied as long as the center of gravity pending the determination of limiting loads. The project has required and demonstrated the transferring CAD and flight simulation packages between different university teams essential as we go forward. Thus, we have mainly demonstrated an effective and quite inexpensive mode for developing such a mission through collaboration between different universities at undergraduate level. Lastly, we are grateful for the partial material support provided by the Taksha Institute. Thank you.